Okay, a very warm welcome everyone to this little recording of mine. This is a recording of a talk I gave at ASC 27. That's a conference that took place in July in Tokyo. And I really enjoyed the conference and I really enjoyed the talks. And the reason I thought that I'd re-record this and make it available is that it contains a few updates on my work on model computation and its relation to consciousness. So yes, thank you very much for clicking on this talk again. This talk was took place in the context of a symposium at ASC 27, which was called Blueprints for Machine Consciousness. The fundamental idea behind that symposium was that famous old credo, I can only understand what I can build, basically. So the idea was to put forward a few attempts towards actually engaging with machine consciousness proactively. As you will see, my talk is probably the critical talk. I should say that I really enjoyed the symposium. It was co-organized by Lenore and me, and we also invited Ryota and Yosha to give updates, and it was really a highlight, as was the whole conference. So thanks again to the organizers. In the symposium, we tried to put forward and then answer some of the questions you could have about AI consciousness. Here are a few, there are more. This talk is only concerned with a small fraction of those, of course. So the basic idea behind the symposium maybe, and also this talk, is that if we think that consciousness is a computation, which is very, very roughly a characterization of computational functionalism, we'll come to that later, then we can ask which computation it is and how can we build that. And of course, one way of approaching then the whole blueprint question is to consider theories of consciousness or models of consciousness, or maybe comparative approaches to pin down in the class of computations. We'll talk about what that is also in a second. To pin down in the class of computations the computation that is consciousness. Yeah? So I'll be denoting it by C star. And that is, I would say, those are the main approaches. Now, what I'll present here is research that somehow takes a slightly different approach, maybe not too different from other work, but at least slightly different. And instead of basically asking directly, like, which computation is it if we presume computational functionalism, which I should say we don't have to, this is just one choice of many. This is basically asking which type of computation, and then maybe that will help us to at least constrain the possible computations that consciousness could be, and thereby also constraining the possible answers for how one could eventually build conscious systems, or also the possible answers on whether the systems we have can be conscious at some point. Okay, so which type of computation? So I guess you're probably all aware of the two major types of computation, analog computation and digital computation. We'll talk more about both of them in a second. There are a number of subsets. There are various different distinctions between those computations that I won't go into. But the proposal in this talk, and I hope to give some evidence for it, is that maybe there's a third large pillar of computation that was introduced by Geoffrey Hinton in 2022. And maybe that is what we have to look at when we look at consciousness. And that notion of computation is called model computation by Geoffrey Hinton. And the big question, of course, is what is model computation? So let's go through these notion of computations slowly. So you're probably all aware of analog computation. Oops, this is going slower again than it should. It's supposed to be a video. I should really, so let's see. Why? Okay, again, is the video starting now? Well, technical problems even when it's recorded after the fact. Well, let's see. Maybe PowerPoint will get into the playing mode in a second. So you probably all know analog computation to some extent. So what this video, which is supposed to play soon, illustrates is a device that was found probably approximately 100 years ago in the ocean. It's called Antikythera mechanism. And it was dated back to ancient Greece, about 70 to 60 BC. So what that device is, and I think yeah, there we go. Now hopefully you can see it slowly playing. Yeah, there it comes. So what this device is really is a device that can be used to predict or to calculate the motions of the planets around the Earth. You'll see a rendering of it in a second. And it was as far as I understand, it was a revelation, our understanding of computation and its backgrounds in human history. So here you can see a rendering of the device. The stones are just how they found it. This is how the device really worked. So on the right-hand side here, you had the output, and then you had this fine mechanical system that was used to produce the orbits of the planets and the positions. So if we, that's an example of analog computation, and we'll look at another slightly more simple example in just a second. But fundamentally, what's happening if one builds such a device is that one needs a notion of inputs, of course. Those are the settings, the times you might be interested in, for example. And then one has a notion of outputs. In this case, the outputs are the positions of the planets around the Earth. So here you can see the user interface, so to speak, of the device. And of course, we're interested then in the relation between the inputs and the output. And that relation is defined by what you could call a theory or a model that defines the problem class. In this case, some understanding of the orbits. I said orbits, I should say really, orbits has this spatial characteristic. I really mean the times and positions of the planets. So that would be the theory or model that defines the problem class. And of course, that's also always something we need if we're interested in computation. But then in addition, what happens here is that one builds this device. This is, by the way, an X-ray scan of the whole thing. One builds this device in order to produce, given some inputs, the corresponding outputs. And the crucial point that I'd like to make here is that in order to build that device, one not only needs a theory that defines the problem class, but one needs some sort of theoretical understanding of the computation device. So in this case, it would be the mechanics, the ratios of translations of gears and all of these things, and it's very advanced. So this would be the model or the theory of how the device works, really, and I'll denote it by D here for device. And that's something that one needs in analog computation, just as well as in digital computation. We'll come to that. So let's consider another example where hopefully there's just a picture, so hopefully things should go smooth right now. And another example is this device here, which is called harmonic analyzer, and that was built by James Thomson in 1886. So what this thing does is, it is an analog computation for something that's called Fourier decomposition, if you might know this from mathematics. Roughly speaking, the idea is you have some function and you want to decompose that function into, at the very least, the most important contributions in terms of sinusoidal or cosinusoidal waves. So what you see here is the device, and I'll just explain it for those interested in like on a very high level. So basically, this device consists of a rod here. You can see this rod. And this rod is feeding in the function as a function of time, right? So I should say maybe it was used, so this was an important problem to solve because of tides. It's very hard to predict the tides. They don't only depend on the position of the moon, but they also depend on geographic factors. So it's very difficult to predict the precise tides. And that was important for commerce and unfortunately also for war. So it was an important problem. And one way to come up with a good model of the tides at a particular place on Earth is to record the tides and then do a Fourier decomposition. That works reasonably well. So the idea was that this device could be used to carry out a Fourier decomposition. So one would have a function, which is just a function of the tides over time, and one would feed that function with some speed up into that system. And that would move this rod here back and forth. And what you see here is that the motion of the rod is transferred to a couple of these devices. So here we have 8, I believe, or is it not 2, 3, 7? 7, I believe, of these little devices that are also displayed down here. And what those are mechanical integrators. So they can integrate a function. And it works like this. So this plate in the back here is spinning at some speed. And this ball here is transferring the motion of the plate onto this little cylinder here. But of course, how much of the motion it transfers depends on where it sits. So if it sits in the exact middle of the plate, it would not transfer any motions because the plate would spin like this, but the ball would just sit on top of it. But if the rod then that feeds in the function would move the ball away from the center of the plate, then more and more of that motion is being transferred onto this cylinder. And maybe you can see that this corresponds roughly to integration. So integration is basically calculating the area under a curve, and you can do that in that way. So the idea would be, just to say it again, the rod would move back and forth according to the values of the function, and then that would determine how much of the rotation of the plate in the background would be transferred to this cylinder here and then being recorded down here. So that is a mechanical integrator. And I wanted to bring out this example because it illustrates this fact again, which maybe is obvious to some of you. So there's the theoretical model that the theoretical problem that we want to solve. So that's TR. R stands for reference. In this case, we want to do the Fourier decomposition, and then we need the device to solve that problem, but we need a model or a theory of how that device works. In this case, again, mechanics, so we need a mechanical understanding of something like the angular speed of the blade, and how we transfer that onto this cylinder in such a way that it corresponds to integration. And the same story holds true for digital computation. So here's a sort of a description of these layers, which your computer that you're using right now has. So there's on the very bottom, there's the layer that you just described, just the pure physics. You can think about that what you want. You could say, well, maybe it's quantum mechanics, maybe it's quantum field theory, anything in that realm. And then based on the physics of quantum theory, in fact, there's the description of the device in terms of transistors. Transistors in all modern computing architectures are quantum things. They are built with semiconductors and they make use of quantum effects. And then you can also sort of abstract away from the transistors and just describe the gates, ignore the actual physical layout of the devices or the transistors. And then on top of the gates and the registers and all that, there's another, so it's another layer of abstraction. There's what's called the microarchitecture. That really defines your processing unit, if you will. And then if we go from the other side, there's the algorithm you want to solve. There's the programming language in which you write the algorithm and its compiler. It might compile to assembly language, which is a low-level programming language. But ultimately, all the programming that you do ends up being compiled into machine code. So machine code is the actual code that's being sent to the processor for execution. So it's usually represented with zeros and ones, just so there's a little bit of information like what the function is that the processor is supposed to carry out, and then there's information about the input data. Maybe you have one piece of input data, maybe two, all of them in zeros and ones. And the link between the microarchitecture, so the highest abstraction, if you will, of the actual processor, and the machine code, which is sort of the lowest level description of the actual algorithm, the link is provided by the instruction set architecture. So if you buy a processor, if you were to work at some sort of company like Dell or Microsoft or Apple or something, you'd buy a processor and you'd get the instruction set architecture, and you could then, there's actually just a few out there, and usually I think maybe only two major ones or something, but you'd have the instruction set architecture, and with that architecture, you could then define what happens if someone were to compile a language into machine code. That's at least a very rough characterization. So the instruction set architecture really, which tells you sort of which instructions are there on the processor and how can I actually get it to do any specific instruction or carry out any specific function. That really is the separation between hardware and software in the usual information theory or computer science slang. And so if we look at this again in terms of this diagram, we have a similar situation. We have a set of inputs and a set of outputs. Usually the inputs are just numbers and the outputs are like results of computable functions applied to numbers in this context. And again, we have a device that is responsible for turning the inputs into the outputs, right? You want the processor, for example, to carry out an addition, or you want to do matrix multiplication or anything like that. And the point I'd like to make is just the same as on the last slide. And maybe here it's much more obvious. In order to do this, in order to build a device that carries out the particular problem class we're interested in, we have to, again, use a theory or a model of the computation device. So that's down here. So in the same way as we did with analog computation. The difference really is that here we have sort of this in-between layer, which you could think of as Boolean logic. It's just, in the end, it's a theory model of computation, Church-Turing-Gödel computation, usually, that somehow allows us to separate what's going on in the device down here from the actual problem class. And we'll come to that specific separation in just a second. That's intimately connected to what happens here. But the important part is still that we need a model or a theory of how the device works. And now if we compare these things, now comes the big turnaround, maybe in history. And that is the notion of model computation that Geoffrey Hinton, who now also won the Nobel Prize, amazing, introduced in 2022 in this paper here, in section 7. So obviously he didn't think it was a very important idea maybe, but I think it is. So model computation is a notion of computation that is very different from the computations that we just saw. And what I'll do on this slide is I'll present some quotes I took from Hinton that helped me in sort of trying to gauge where he may be wanting to go. And I'll just present them to you. And then on the next slide, I'll tell you what I think that could mean. So let's look first at immortal computation. So that is the opposite of mortal computation. Here are some quotes from that paper. So immortal computation is the idea that software should be separable from the hardware, that the same program or the same set of weights can be run on a different physical copy of the hardware. And he says that immortal computation makes the knowledge contained in the program or the weights immortal. The knowledge does not die when the hardware dies. And that's, of course, intimately connected to this notion of universality in computer science. So the idea is that a computation is immortal if we can move it from hardware to hardware somehow. In contrast, the mortal computation is characterized in this paper as follows. We can allow large and unknown variations in the connectivity and nonlinearities of different instances of hardware that turn a computation into something he calls mortal computation. There are parameter values that are only useful for that specific hardware instance. And ultimately, then the justification for this specific choice of term, which is of course very interesting, is that he says those are computations that when the systems perform these computation, these are computation which are mortal in the sense that they die when the hardware dies. They cannot be separated in a sense from the hardware. And the typical example we might have in mind are, of course, sort of biological brains. Like even if you could somehow copy at least the states of my neurons to another brain, that wouldn't imply that the other brain were functional, because there's large and unknown variations in the connectivities, there are non-linearities in different brains. So that is at least the intuition. And I think in the paper, there's only a few paragraphs about these things. So there's like, we have to do some work in order to understand what it is that is actually being pointed at. But Geoffrey Hinton is very specific in the paper, at least, in sort of claiming the relevance of this. So he says the research community has been slow to comprehend the long-term implications of deep learning for the way computers are built. So the suggestion is that maybe this notion of computation is what we'll see in the future. And I think I'm very much convinced by that suggestion. Maybe we can talk about it at the end there's no time limit, but if I don't forget. So I think there are indications that we're moving into that direction already. But okay, so here are these words, these characterizations. So we have to think about what is it that could actually be meant in this context. And the purpose of this talk is to propose a further step relative to what I have published in this small piece I'll discuss later already. In the small piece I've published so far, I've really used sort of this distinction to say, well, let's define mortal computation in that, sort of trying to formalize this distinction, then run with that. And that's already rather interesting what you get. But what I want to do now is I want to suggest a further thought that I've developed together with my good friend and co-author Tim Ludwig. And the thought is really this. So let's compare again. This was analog computation. This was digital computation. So what is really crucial to these both forms of computation is that they require this model or theory of how the device works. So if you think a little bit about this notion of mortal computation, also the example biological brains, and what's happening in the semiconductor industry and some startups right now, well, at least you could think about the hypothesis, and I should say that's not Geoffrey Hinton's hypothesis. Oh, there's a little bit more input because before the final point comes. So if you think about what's happening, and then also some quotes like the hardware whose precise details are unknown, or that mortal computations rely on a learning procedure to discover parameter values that make effective use of the unknown properties of each particular instance of the hardware. Both are from this quote. Well, then you could think that maybe mortal computation is actually model-free computation. So that means computation which doesn't require a model to be implemented. You would still have a device that carries out the computation, but the device would be configured based on, or selected based on training, based on optimization tasks, maybe based on some sort of natural selection. And there wouldn't be a model that someone uses to build the device. And that somehow there wouldn't be a model that ensures that the device adheres to the problems in the problem class TR. So that is at least a thought one can think. That would be an explication of what Hinton is writing that goes beyond what he himself is saying. And what I want to do is, in this talk really, I want to indicate that model computation, understood in this more minimal way that I'll hint at or point at in a second, but also maybe in this more full way, could be exactly what is needed for consciousness if consciousness is a computation. And I will not be able to really give a very conclusive argument, but I'll be able to give 3 indications thereof. I think that's more something like a triangulation, just because I have 3. So the first is related to computational functionalism. We'll talk about that in a second. The second is related to something called verification and the design of processing units. The CPU you have in your phone or computer right now, but also the GPUs or TPUs or DPUs that are being used in AI research right now. And the third one is then connected to evolution. And I should say that this talk was for the symposium. It was supposed to be, I think, 20 minutes long or less. So I'll really only touch on these things briefly, but I'll tell you where you can read more if you wanted to. Okay, so before I do so, I have to give a little bit of a very short how do you say this? Like, is this called intermezzo or something, or interlude? So most of my results take the form of theorems, and that might be very unusual for people in philosophy, in some parts of or most parts of philosophy, and probably also in the sciences. So usually you say that if somebody is working without theories, in the specific scientific sense and without empirical data, well, then they probably use arguments. And that is true to some extent. But there's also people who use theorems. And most of the people who are not in the part of philosophy that's called mathematical philosophy or in any form of sciences, they react a little bit like this when they see theorems. So I thought I'd just explain this a bit. So the idea is that you can prove things in the same way that you can argue for things. But there are differences. So in arguments, for example, good things that they are usually directly comprehensible. They might have 3 or 4 premises or something in philosophy. So you just get the premises. You then have to think very carefully about whether you really agree or there's some sort of loophole, but they're directly comprehensible. And another sort of pro is that in arguments, if you look carefully in justifications, it is somehow permissible to waive trees of the possibility tree. So you could just sort of discredit or unsuggest a particular option that you cannot conclusively exclude. So those are pros for arguments. It allows us to go a little bit further than if we had to go carefully through every possible leg of the possibility tree. The cons is that in argument, usually the conclusion is deductively close to the premise. There isn't such a large distance. That's why you can get it directly. And of course, I mean, you probably heard that in my tone a little bit. It is also a little bit problematic that you can waive legs of the possibility tree. Theorems, on the other hand, have a larger distance. So the pros are they have a larger deductive distance between the conclusion and the premises. There's a proof, and in many cases, in general, in many cases, you have to go through the proof carefully to see why the result holds. And in very good cases, like Bell's theorems, for example, you might go through the proof 5 times because you can't believe that the result actually holds. And the pro is also that there is the need to strictly exclude all legs of the possibility tree for a theorem to hold. So you have to either exclude it by making assumption implicit, very explicit, or you just have to work hard to try and find ways in which the possibility cannot occur given the assumptions you have chosen. The cons is, of course, that there are formal assumptions that feed into the theorems and they have to be carefully checked. So what I'm doing here is very reminiscent. So there are many theoretical results in mathematical philosophy. And what I'm doing here is very reminiscent of I hope the smiley changed. I hope you're feeling better now. And what I'm doing here is really very reminiscent of the use of no-go theorems in physics, specifically in the foundations of physics. So no-go theorems are a very important part of the scientific methodology in physics. They're used to make progress in theoretical and conceptual domains, I think it's fair to say. So basically what they do is they have some premises that are formalized and then they prove a current result. And that might be a result that helps us in making new theories or helps us in guiding where to look for new theories or helps us in understanding theories or helps us in understanding what certain systems can do. So there's a broad range. And so at least 2 of the 3 corners that I'll introduce to you, that I'll show you now, are no-go theorems in that sense. Okay, if you want to use why mathematical methods are relevant in philosophy, for example, I really recommend this very small piece by Hannes Leibgate. It's called Scientific Philosophy, Mathematical Philosophy, and all that. Okay, good. Back to the main story. So here's our triangulation, and now I'll introduce each of these corners of the triangle rather briefly. And the first is computational functionalism. And let me just get straight to the point. So this is a result I've shown. It's a theorem, and the theorem has two premises, and it has one conclusion. So the first premise is computational functionalism. Roughly, that's not really correct, but roughly the idea that consciousness is a particular computation. If you're interested, you can check out the preprint I have right now, where I give the exact formal definition, exact conceptual definition provided by Putnam. But that's the rough idea. Computational functionalism is true if and only if consciousness is a particular computation. And the other premise says that all immortal computations are also Turing computations. That's a premise we have to make. I think it's implicit in what Hinton is saying, but it's a premise you could theoretically drop. And the result is then showing that if both of these premises hold, then the specific computation that is picked out by computational functionalism, which we already had on the first slide, or third slide, this is this computation C star, well, then that has to be a mortal computation. This is the theorem. There's one other assumption, which I think must be obviously true. If you're interested in that, please see the paper. Also, the very short proof is in the paper. Here's a QR code, and here's the paper. It's online. I'll probably update it a little bit in a little bit, but currently it's still what I think is true. Okay, so that is the first indication for why I think that mortal computation could be relevant. And I should say, so the reason I wrote this up when I found out is because I found that somehow funny, because I think almost everyone, when they talk about computational functionalism, they might have Turing computation in mind. I did certainly before I started to do research on this topic. So it's kind of funny that very mild assumptions already force one to consider another notion of computation. And I should say mortal computation includes many other notions that have been proposed so far. For example, neuromorphic computation suggested by Neil Seth after this talk at ASSC, and probably a number of similar concepts. The idea is really, what I like about the notion of mortal computation is really that might be a new line that can be drawn in the vast big classes of computations we consider. Okay, so I found it kind of funny, so I wrote it up. And I've gotten a lot of feedback, also of criticism, and the only criticism I still to this point see as valid is to drop this premise. And I think that's actually one I didn't get, but this is all the others I think are fully accounted for. But this is basically a conceptual choice that's implicit right now in the notion of immortal computation, according to Hinton. And maybe I should also say at this point, so this paper does not presume this model-free notion I've introduced just in the beginning of the talk. This is really just making use of what could be called a definitorial, I think that's the word I used, definition. No, sorry, I used a different word. Well, anyway, a definition that basically defines something by saying it what it is not. Let me know if you know a good word for that in the comments, or if not, you can see if you like the word I used in here. Okay, good. And as I said, this is the big question. Is that valid, that assumption, or not? Okay, this was already the first triangle. So let's look at the second. And the second has to do with something that's called verification and processing unit design. So PU stands for processing unit, like the CPU in your computer right now, or the GPU in your computer or phone right now. That's what it is. So the result starts from a premise, and the premise is the following. It's that, and I would argue for it very strongly, I really believe in it. It's the premise that a necessary condition for investigating consciousness scientifically is that consciousness makes some difference to a system's behavior or report or actions. So why is that true? Well, the idea is if you want to find out how consciousness relates to the brain, say, you gotta have some anchor where you can anchor your theories and your data on. And usually that's report. We have to, at least in some instances, believe that if someone says, I see red, they actually see red, right? Or we have to believe that if someone reports that they saw a stimulus consciously, that's because they saw the stimulus consciously. That's the underlying intuition. The big question, of course, is what do we mean by difference, right? One could think about causal influence, but that's not really what we want. Certainly not necessarily, at least, certainly not necessarily in a non-physical sense. That would be an example, but that would be way too strong. That can't be a necessary condition. We could also say, well, maybe it's the difference between the system being conscious and the system being not being conscious. But also here, that's not a very good example, because there might be some systems in specific states that just cannot be not conscious, according to the correct theory of consciousness that describes reality. So I think the right choice to actually render this a necessary condition for investigating consciousness scientifically is that you have to think about the difference between the dynamics. Dynamics here is just a short term borrowed from physics for a system's behavior, reports, or actions, or anything it does. So we have to think about the difference between the dynamics of a system as specified by a theory of consciousness and the dynamics of a reference theory about the system that does not include consciousness. So that might sound like a little bit of a mouthful, so let me try to explain. So just think about the brain. We understand how the brain does information processing, we understand motor output, we understand verbal output. Now think of a neuroscientific theory that's supposed to explain why, for example, there's a particular eye blink response in certain conditions. Maybe when you give a puff of air to the eye, there's a certain eye blink response. And that theory, if it doesn't include consciousness, would be a reference theory. It provides an account of some of the dynamics of the system independently of consciousness. Now, if we now think that consciousness is actually sort of there are facts about conscious experience, and therefore we need to explain them, and therefore we need theories about how these facts about consciousness relate to facts about the brain or what's happening neurally, well, we need to bring a theory of consciousness to the table. And the point would be that we cannot test whether that theory is right or wrong or how it compares with other theories of consciousness if that theory doesn't somehow make a difference to the story that the purely neuroscientific theory just told us, right? So somehow the theory has to explain why it is the case that if you apply a puff of air to an eye blink, to the eye, there's a slightly different eye blink response if a subject experienced something consciously. That goes under the name of no report paradigm, and that was not a fair summary, just a very, very messy indication of what it is. But there's in fact a way to test whether someone experienced the stimulus consciously by this sort of methodology. And if the theory of consciousness is supposed to be understood scientifically or tested scientifically, or at least sort of if its predictions are supposed to be checked scientifically, and the theory needs to somehow explain why there is a difference relative to the neuroscientific story of eye blink response. It needs to make this explanation, at least in principle. And this is the necessary condition here. I hope it's clear. If not, please let me know in the comments and I'll try to answer if I can. So you can take this and you can formalize this. So because a system's behavior or reports or actions are called dynamics, a system's dynamics, we're just going to call this dynamically relevant. So we'll say that consciousness is dynamically relevant according to some model or theory of consciousness M with respect to the reference theory if and only if this conditional here holds. And the essential point is if the system is conscious in a particular trajectory, then there's at least some difference as far as the things are concerned that the reference theory can explain between the trajectory that the model of consciousness prescribes and the trajectory that the reference theory prescribes. That's a formalization of this thing. And I would claim that's a necessary condition for the scientific investigability of this model or theory of consciousness. Fundamentally, again, the idea is just that the system says it's conscious when it's conscious. That's something that a theory has to bring into the neuroscientific story of information processing in the brain. And the point is, I like this condition because it's much weaker. So if you think consciousness has a causal influence, independently of whether you think that consciousness is physical or not, well, then it must make a difference. Or if you think that there is actually a difference between, there is actually sort of the possibility that the system is always experiencing, doing the same thing that if there's actually the possibility that the system is doing the same thing consciously or unconsciously, then you think that consciousness does not make a difference. So what we can do is we can run with this condition, and we can now add in another fact, a second assumption. And that assumption has to do with verification, what's written up here. So building processes is a really complicated enterprise. You probably knew that. And it's extremely expensive nowadays. So if you make a CPU, that's the central processing unit or graphics processing unit or tensor processing unit, there's a number of very expensive steps you have to run through. And an important part of at least 2 or 3 of these steps is a process called verification. And what it does, it ensures that the dynamics of a system that you're building adhere to what is specified by the computational theory, basically Church-Turing-Gödel computation on computable function, or in other words, the instruction set architecture. So you want that whatever you're building in one of these semiconductor fabs does what it's supposed to, and that's a very expensive process that's called verification. And just for reference, like there was one big mess up. There was actually, I think 1997, there was an Intel Pentium chip that messed up division of numbers. Like I don't remember, but like sort of on the, like several decimal points in. So it didn't matter for you or me, but it mattered for corporations. It mattered for science, of course. So that was a problem of the chip that occurred because there was a failure of verification. The chip didn't do what it was supposed to do, and that cost Intel back then, I think, $500 million. Even so, only a small fraction of the users were affected, and even so, a small fraction of users actually wanted a replacement chip. But so you can see why this is so important and why so much effort is put into this. So graphically, I can illustrate it maybe like this. Think about error correction. So let's say you want the system to be on the pink curve, and then if the system actually goes onto the yellow curve, the hardware has some sort of error correction codes. That's only a very, very small part of the whole verification thing that push it back onto the yellow curve. That's the idea. And you can formalize this too. I won't go into details right now. So these are 2 conditions that drop out of the formalization of what verification means for processes. Before I go on and then tell you the result that you get with these 2 formalizations, I should emphasize, so this is really intimately connected to immortal computation. Yeah? Only because we ensure that all of the system are exactly the same as far as the computational theory is concerned, can we then actually move around our software? Can we write one piece of software locally here and then run it on a million devices all over the world? Note that, so I would say that immortal computation implies this. The problem that got me thinking so deep also about other things is that it's not the other way around, as far as I understood immortal computation back then. Anyway, so you have these 2 assumptions, dynamical relevance and then verification, and you can then provide a no-go theorem as indicated regarding AI consciousness. You can prove that if consciousness is dynamically relevant, then AI systems aren't conscious. And if you're looking for the proof or the details, this is joint work with Tim Ludwig. You can check out this preprint, or you can just Google it. So the thing is now actually called the case for neurons and no-go theorem for consciousness on a chip. This QR code is linking to the previous version. We'll update this soon, which basically has the same math, but so some fewer explanations. And I think we didn't explain the whole no-go theorem part in that version. You can see, but the math is all the same. Yes, so that's something we're able to prove. And the idea again is that, first of all, I should say, this is a no-go theorem. So it's very tempting to try and provide some intuition to you when you're probably thinking about intuition. And that's great. But the problem is that if you then criticize us on the basis of that intuition, you're basically neglecting the power of formal approaches, which is fine. And I'm very happy to react. Please put your criticism out. But still, I just want to emphasize this. There is something that formal results can give us that is not available to intuition, which is one reason why I like to work on them. Okay, so that's the verification part. So we've seen that just because of the way verification is built and making use of this necessary condition, we basically get a result that shows us that contemporary, at least, AI systems are not conscious or cannot be conscious. Okay. And so these 2 are, as I said, formal results. And so someone I hold very dearly, whose advice I hold very dearly, recommended to me that I shouldn't work with these formal things too much. So in this talk at AC, I at least wanted to include some preliminary work, which would, at the present point at least, be more on the side of non-formal or conceptual result. And that has to do with evolution. So let's look at this real quick. And I really like it. That's work in progress. So please send your feedback or your criticism By the way, you can also send, I think in science, we're not very often very positive. So if anyone has some positive thoughts, of course, I don't mind if you put them out or send them to me personally. It's always happy to hear someone thinks one is not completely on the wrong track. Okay, anyway, back to the story. So evolutionary game theory. Evolution, sorry, I should say, so this is a result regarding evolution and specifically evolutionary game theory. So let us use the symbol big S or the letter big S to denote an evolutionary strategy. So that's something like a set of abilities that you can have. And then as customary in evolutionary game theory, let us denote by pi of S, comma S prime, the payoff, abstractly speaking, for the strategy F when it is competing against the strategy S prime. Okay, and what we can do with just these two notions, we can make use. So first of all, we can bring consciousness into the picture. We can say a conscious evolutionary strategy is an evolutionary strategy in which an organism is conscious. Yeah. So it means it has the ability to be conscious and then also makes use of that ability. That's just the definition. Maybe I should also throw in, it's not good if I throw in too many things, but I'll just throw in this. So evolutionary game theory can be applied to evolution. It's not just about a game theory, but as I understand, it's called evolutionary game theory because it has its origin in game theory. And it's applicable here, it's interesting here, because it's formalized. So it allows us to talk about evolution with some sort of formal precision. Okay, so we have these three notions so far. So what we can do then, we can make use of a notion in evolutionary game theory that's called locally superior. So let me introduce it first and then tell you how we relate it or how it relates to, how we can define its relation to consciousness. So an evolutionary strategy S is locally superior if the following thing holds. It's locally superior if there's a neighborhood U of S, that means an area around the strategy S in the abstract space of strategies, such that the following condition holds. For every strategy in the neighborhood that is not the strategy S itself, it is the case that the following inequality holds. So on the right hand side, on the right hand side, we have the payoff that you get when the strategy S is playing against itself. On the left-hand side, we have the payoff that you get if the importantly, this is the strategy S prime. That's the strategy in the neighborhood, one of the strategies in the neighborhood. On the left-hand side, you have the payoff that you get when the strategy S, that is locally superior, plays against that strategy S prime. And what that inequality is showing is that the payoff, the evolutionary benefit, if you like, of the strategy S when it plays against S prime is larger than the evolutionary payoff if S is playing against itself. So the fundamental idea here is that you have a world that's populated of entities that follow the evolutionary strategy S prime, perhaps because that was the ideal strategy before. But then if the locally superior strategy S comes into play, then that outperforms the strategy that is being played by the agents. That's the meaning of local superiority in evolutionary game theory. Now what we can say that consciousness has an evolutionary advantage. This is the meaning behind locally superior. If and only if there's at least one conscious evolutionary strategy that is locally superior, right? So we're saying the concept of consciousness has an evolutionary advantage if there is at least one organism that has the ability and makes use of the ability of being conscious, and that is also locally superior. That is the definition here. The strategy that it uses is locally superior. Okay, so let's just make this a premise. Yeah, what I just said, no change here. We'll just move it up, make it a premise. And now we're going to add a second premise, and I'll tell you a couple of intuition pumps about the second premise in just a second, and then we'll actually provide a little argument for why the second premise should hold true. So the second premise is that no digital model-based computational evolutionary strategy can be locally superior. So let me first of all explain it. So digital model-based computational evolutionary strategy basically means that it's an evolutionary strategy that is being implemented by one of these by the digital model-based computation that I had in the beginning of the talk. Basically, it's implemented by something that has the ability to run Church-Turing-Gödel computations. That is the idea. And the premise says that none of these systems can be locally superior. So first of all, intuition pumps. Why should this be true? No. First of all, what follows if it were true? Well, if we just combine these two premises, we immediately get that if consciousness has an evolutionary advantage, it cannot be a digital model-based computation, meaning it cannot be one of these devices we called digital model-based computation on the previous slides, and that includes sort of any computation that's currently running on your computer or on your smartphone, and that includes any of the computations that are currently running on any of the data centers that run large language models. Changes are coming, maybe I'll talk about it in a minute, but at least as far as the current generation and also probably the near future generations are concerned, that result will show that they cannot run consciousness even if consciousness, they cannot run consciousness even if consciousness were a computation. Okay, so why should the second premise be true? Well, here are the intuition pumps. Well, first of all, there are these huge energy requirements, right? Like if you think about it in evolutionary context, you need so much energy to do the same thing, like even just language by an LM, as compared to like what we all can do with 20 watts or what that the brain uses. So that's an intuition for why these things can't be locally superior. They just need too much energy to run. Another requirement could be the resources for the construction. It's extremely complicated to build a CPU. I mean, this you know it's high tech, but it's absurdly complicated. So much more complicated that there's only a few places around the Earth. I don't know how many there are right now. I mean, there may be 3 companies that can build the last generation processing units, even for your phones. 3 nanometers or something. The current generation is very small. So then another intuition pump for these results is that universality may not be selected for in evolution, right? At least if you think about natural evolution, you could say, well, there are all these tasks you have to solve to basically survive, and it doesn't look like universality is one of them, or at least it's likely not one of them. Universality being the idea that you can solve any problem that's solvable on any computer. Yeah, that might not be required. It might be fine if you solve the problems that really matter for survival really quickly. And another intuition pump is closely related. It's over-engineering. It's the idea that when we actually build something when we simulate, for example, some human behavior or whatnot, or when we build something on a computer, we usually have to over-engineer quite heavily, both on the hardware side and the software side. An example of what I have in mind here are these startups right now that are starting to emerge, which are trying to say, well, let's use let's take the huge amount of matrix multiplications we run on large language models. Sorry, I should say the large number of matrix multiplications we have to run when we run large language models. And currently these are run on code. So they go through the whole hierarchy that we had on the other slide, right? Someone programmed what happens, and then it's going to be fed down to the instruction set architecture. And then the computer is carrying out a ton of little functions to actually multiply these matrices. And the startups are saying, well, why don't we just take these and just create a hardware chip that is doing this matrix multiplication? So that would be a first step. That would not go towards model computation as of yet, but it will go towards analog computation. So the idea would be that there's a huge amount of over-engineering involved if we just run the LLMs on digital model-based computational devices, as compared to at least just model-based computational devices, which are not digital anymore, which don't have this. That's maybe not a good term, I'm thinking, but the term I used here, but which don't have this Turing computation layer in between. So these are the intuition pumps, but we can actually also provide a little argument centered around the third intuition pump. And the argument would go as follows. So we could say, well, so it's an argument for this premise P2. Or you can first of all say, well, a digital model-based computation evolution strategy is a strategy which has the ability to solve all problems in CF, CF being the class of problems on Turing computable functions. That is what I think what I take digital model-based computation to mean in this context. As I just said, maybe I need a better word for this. Second premise could be called fitness, just as a title for the premise. We could say the ability to solve all problems in CF is not selected for in evolution. That seems at least a plausible premise. And the third one could be selection. What is not selected for in evolution cannot be evolutionary stable, right? It would disappear. That seems a general principle of evolutionary thinking. Now, if we make use of these 3 premises and the following theorem, in evolutionary game theory, which was proved by Hofbauer et al. In 1979, which basically says if an evolutionary strategy S that is locally superior if and only if it is evolutionary stable. There's a formal notion of evolutionary stable in evolutionary game theory, and it tells you that these two statements are equivalent. So if you combine all of these premises with a theorem, we get the premise P2 of the main argument. No digital model-based computational evolutionary strategy can be locally superior. And therefore, we also get the conclusion. If consciousness has an evolutionary advantage, it cannot be a digital model-based computation. Does it have an evolutionary advantage? There are good arguments for it. So, for example, would be very surprising that it appears to be the case that all the systems that made it in evolution, so to speak, or most of them at least, are conscious. So it's arguable that it at least has an evolutionary advantage, but of course we can't know for sure. Okay, so what I'm thinking is that this digital model-based computation is basically, or any evolutionary strategy that is based on digital model-based computation, is basically restricted to a subset of all possible strategies. So the idea would be like, I don't know if that picture is meaningful to many people, but the idea would be that if you're actually making use of digital model, so the red ball is TR, the sort of, well, let me just try to explain roughly. So the idea would be that if you're sitting in a digital model-based computation and then sort of are restricted, you want to react to evolutionary changes, right, or to threats or whatever. Then you can react, but you can only react in certain ways, and they're sort of the digital model-based computations are restricted to this subset of all changes that you could make. You cannot change your hardware, at least in arbitrary respect. You cannot change the fact that you're universal, so you're restricted to that subset. The subset is great, it makes you universal, it allows immortal computation, but it restricts you from making certain reactions to certain threats that you would need to make. Don't know if that picture is very helpful. In general, it's very helpful for me, even so on a very intuitive level still, as you can see. Yeah, so there's the third thing. The question is, of course, well, can we turn that into a theorem? For me, I would only be satisfied by that if that really were a theorem where we can spell out very exactly like what are the exact assumptions, how exactly do we define digital model-based computation in a minimal sense so that we have a theorem that establishes this conclusion. But as I said, I wanted to share this first of all because currently it isn't, so that might be a good thing, more accessible. And second, I'm very curious to hear what people think. Objections, also if you like it, let me know. Okay, that was the third part of that triangulation. I'll just read it again. The conclusion of that argument was that if consciousness has an evolutionary advantage, it cannot be a digital model-based computation. Needless to say, these things don't integrate as of yet, right? This one presumes as a minimal definition of model computation. They don't really understand how these relate specifically or in full just now. So it's an ongoing process, and I'm curious to see where it goes. Okay, let me just wrap up. First of all, here are the 3 points that I made. So first of all, model computation is a new type of computation. That was an important point I wanted to make. It was invented by Geoff Hindrey, and I think it might become relevant in the context of AI and large language models, as Geoffrey Hinton thought, at least back then. And I think we're seeing this already. We're seeing semiconductor developments that go away from immortal computation. Not so much in the exact way that mortal computation was characterized by Hinton just yet, but at least they use things like reproducibility. They use things like there's an error rate that's being accepted for fast computability, things like that. And we're also seeing this on the software side. So I can very, very much recommend Andrej Karpathy's talks on how large language models might be something like very early operating systems, like analogous to the very early operating systems we had maybe in the 70s. And they might really become the operating systems we use in the future. So these things combine to actually let me think, at least, that model computation might be the future of computation in society, I should say. It will never really, I'm sure there will always be use cases for immortal computation, but it could be relevant. Okay, second thing I wanted to argue for in this talk was that model computation could be thought of model-free computation. Maybe not, maybe yes. This is my best way of currently understanding what model computation could be and what maybe is behind the ideas that Geoffrey Hinton put forward. Yeah, let me know what you think. And the third one, I wanted to argue the main part of the second part of the talk, if you like, is that there's a lot of evidence, in my view at least, that if consciousness is a computation, then it could be a mortal computation. We don't know whether it is. It's an assumption among many other options, but I think that's at least worth considering. So we currently have 3 results under 3 different sets of assumptions, 2 of which are pre-printed and you can read up. Okay, that's it. So thanks very much for the attention, both here and in Tokyo, if you were at that talk. I very much look forward to any questions. Put them into the comments or shoot me an email. Objections are welcome. As I said, don't hesitate to say if you like it. In general, in science, we don't. You don't have to. Sorry, that came across wrong. But yeah, just saying. Okay, good. So that's it. Thank you very much. And I hope you enjoyed the talk. And I look forward to interacting with as many of you as I can in the close future. Bye-bye.